Hello friends, in last lecture we have seen some topics of series. In today's lecture we are going to continue the series. In today's session we are going to check out P series and comparison test. Up to last lecture we have seen partial sum, convergence, divergence, test for divergence and the integral test. Now in today's session we are going to discuss about these two topics, P series and comparison test. So the first we are starting with a P series. P series is nothing but it is an example of a integral test, but we are going to use P series as a standard series in a comparison test. So first of all, for what values of P, series sigma 1 upon n raised to P converges. So for that we are going to divide P into three parts. First one P is negative, second one P is 0, third one is P is positive. Suppose P is negative, in that case 1 upon n raised to P is going to be a infinity as n tends to infinity. Same manner, suppose P is a 1, sorry P is 0, then in that case 1 upon n raised to P will be 1, and if you are applying limit n tends to infinity, then it has a value 1. So in this both case, that means P is negative or P is 0, in both of the case, the series is going to be a divergent by test of divergence. Now, we are going to start with P greater than 0. See, for P greater than 0, fx will be 1 upon x raised to P. Now, 1 upon x raised to P is decreasing and continuous function for interval 1 to infinity because it has a decreasing term. So, we are going to apply integral test. For integral test, first we are dividing P into two parts. Either P is 1 or P is not equal to 1. So if P is 1, then in that case, integration 1 to infinity 1 upon x raised to P, that means 1 upon x dx. That is nothing but we are using the improper integral and replacing infinity by b. So you will have limit b tends to infinity, integration from 1 to b, 1 upon x dx. Integration of 1 upon x is log x, substituting upper and lower limit and then applying limit b tends to infinity will give you the answer infinite. So for P is equal to 1, our series is divergent. Now, if P is not equal to 1, P is not equal to 1, in that case, integration 1 upon x raised to P, where limit is from 1 to infinity. So infinity is replaced with b and again applying limit b tends to infinity, integration 1 to b, 1 upon x raised to P dx. X raised to 1 upon x raised to P has an integration x raised to minus t plus 1 upon minus t plus 1, and substituting upper and lower limit, that will give you 1 upon 1 minus p into the bracket 1 upon b raised to p minus 1 minus 1. Now, here we are going with a cases of p minus 1. Suppose power p minus 1 is positive, that means p is greater than 1. Then in that case b raised to p minus 1 is tending to infinity because b is tending to infinity. Then in that case 1 upon b raised to p minus 1 has a value 0. So in that case your integration has a finite value, integration 1 to b 1 to infinity 1 upon x raised to p dx, that will be a 1 upon p minus 1. That means it has a finite value and therefore your series is convergent for p greater than 1 by integral test. Suppose p minus 1 is negative, then in that case 1 upon b raised to p minus 1 will be going to be infinite as b tends to infinite, and therefore by integral test your series is divergent. So what you have for p less than 1 you have divergent, for p greater than you have convergent, and for p equal to 1 you have divergent. That means now for any value which is less than 1 or equal to 1, for all the values less than 1, the series is going to be divergent. So if we are going to summarize the P series, then P series is going to be convergent for P greater than 1 and divergent for P less or equal to 1. Now we are going on to the comparison test. Now direct comparison test. Here what is a direct comparison test? Now in the direct comparison test, we are going to divide comparison test into two parts. First one is a direct comparison, second one is a limit comparison form. Generally, limit comparison form is the extension version of direct comparison test. Suppose sigma un and sigma vn are two series with positive terms. We are considering that all terms are positive. And if sigma vn is convergent with un is less or equal to vn for every n. That means un is smaller than vn for every n, and the larger series sigma vn is convergent, then the smaller series sigma un is also going to be convergent. Vice versa, if sigma vn is divergent and un is greater than or equal to vn, then in that case the smaller series is divergent, then the bigger series is divergent. That means sigma vn is divergent, therefore sigma un is divergent. So please remember, if the larger series is convergent, then the smaller is convergent, and vice versa. If the smaller is divergent, then the larger is obviously divergent. Okay, because we are considering with a positive term series. Now we are starting with an example. Determine whether the series sigma 3 upon 4 n square plus 3n plus 1 is convergent or diverges. So here un is equal to 3 upon 4 n square plus 3n plus 1. So we are starting with a standard inequality. So standard inequality, we have 4n square is less than 4n square plus 3n plus 1, correct? Because 3n plus 1 we have added on right hand side. Now taking reciprocals, that will change your inequality. So 1 upon 4n square plus 3n plus 1 will be less than 1 upon 4n square. Now multiplying both sides with a 3, that will give you 3 upon 4n square plus 3n plus 1 is less than 3 upon 4n square. Now see here, left hand side is your un, correct? So we are going to consider right hand side is equal to vn. That means right hand side is a series which we require. But in the right hand side we have a series 3 upon 4n square. So sigma 3 upon 4n square can be rewritten in a form of 3 by 4 into sigma 1 upon n square. And sigma 1 upon n square is a p series which we have already seen, correct? So here p is equal to what? 2, because the power of n is 2. That means p is equal to 2, which is greater than 1. And we have already seen that for p greater than 1, this series is convergent. That means your series sigma 3 upon 4 n square, that is convergent. So by direct comparison test, your original series sigma un, that is sigma 3 upon 4 n square plus 3n plus 1 is also convergent. Now we are going on to the limit form of a comparison test. Suppose sigma un and sigma vn are two series with positive terms, and if the limit n tends to infinity, un upon vn is equal to l, where l is any non-zero finite number. See, here it is necessary, it is non-zero and finite. Okay, for 0 you cannot say anything, and if for infinite also you cannot say anything. That means L must be some non-zero finite number. Then both series are going to be converges or diverges together. That means both are going to be convergent or both are going to be divergent. Okay, so if sigma vn is convergent, then sigma un is also convergent, and if sigma vn is divergent, then sigma un is also divergent. Now you have to take vn yourself for comparison test, correct? So here in the form of limit comparison form, what we are going to do, we are going to start with some simple simplification of a original un. For comparison test, we are going to take vn from either a p series or it is from a geometric series. And we are already aware of p series is nothing, it is where it is converges and where it is diverges, it is already known. Same manner for geometric series, we are also aware of geometric series is converges for mode r less than 1 and diverges for mode r greater than 1. So we are going to take vn from this known series, so such that we are aware of whatever the vn we have taken, that is convergent or divergent. Okay. Now Using this, we are going to solve any example of a comparison test. Discuss the convergence of the series sigma 2n upon n plus 1 the whole square. Now see, here un is equal to 2n plus 1 upon n plus 1 the whole square. What we are going to do, we are starting with the dominant term of numerator and dominant term of denominator. Now the dominant term of numerator is 2n and the dominant term of denominator is n square. But we are going to ignore the constant, so I am not taking 2. So we have written Vn is equal to n upon n square. So Vn will be simply 1 upon n. So you have to assume Vn by this method. In the case of numerator and denominator both have the polynomial of n or having some powers of n in numerator and denominator. So here we have taken Vn is equal to 1 upon n. Now we have to find the limit un upon Vn. So applying limit un upon Vn, that will be 2n plus 1 upon n plus 1 whole square divided by 1 by n. But denominator is going to be numerator and that will give you into n. So simplifying the numerator and denominator, so common out n from numerator and n from denominator, that will give you the simple form limit n tends to infinity 2 plus 1 upon n divided by 1 plus 1 upon n the whole square. And if you are applying limit, then you will have value 2. Now see, 2 is a non-zero finite number, correct? So your condition is satisfied for limit comparison form. And sigma Vn is nothing but sigma 1 upon n is a p series with p is equal to 1 because n raised to nothing, that means n raised to 1. So p is equal to 1, then your series is divergent by p series. So sigma Vn is divergent. So by comparison test, sigma un is also going to be divergent. Now starting with another example, test the convergence of the series 1 upon 1 into 2 into 3 plus 3 upon 2 into 3 into 4 plus 5 upon 3 into 4 into 5 and so on. See, here you have not given your series in the form of sigma. So first you have to write down what is the un, that means what is the nth term, correct? Now see, you can see that if you are only considering with a numerator part, then numerator part is 1, 3, 5, 7. That is nothing but it is an arithmetic series with a difference d is equal to 2 and first term a is equal to 1. So if you are going to find what is the nth term, then you are going to use the formula a plus n minus 1 into d, correct? So if you are applying it, then the numerator will be 2n minus 1. Same manner from denominator, we are going to take a first term, then that will be a 1, 2, 3, 4 simply. So that will be simply n. Same manner if you are considering second term, then that will be a n plus 1. Same manner third term will be a n plus 2. So your un will be 2n minus 1 divided by n into n plus 1 into n plus 2. So in such a manner you have to find out what is the nth term of a series. Same now, once you have the nth term un, then we are starting with a dominant part of numerator and dominant part of denominator. So dominant part here of numerator is 2n. Dominant part of denominator is n cube, because if you are going to multiply each, then you will have n cube as a maximum term. So dominant, that means a maximum term, correct? So and we are going to ignore the constant, so you will have n upon n cube. N upon n cube, that will give you 1 upon n square. Now find out the limit, that means limit un upon vn, and simplify. That will give you the answer of the limit is 2, correct? So what we are going to do, simplifying all this term and find out the value, correct? Once you have the value 2, which is non-zero and finite, so your condition of limit comparison is fulfilled. Now sigma vn is nothing but sigma 1 upon n square, and that is sigma 1 upon n square is convergent because p is equal to 2, and for p series p is equal to 2 convergent, and that will give you sigma vn is convergent. So by comparison test, your sigma un is also convergent. Now test the convergence of a series sigma sine 1 upon n. Now see, this series is in a form of trio. This is not given in a simple form. So what we are going to do, we are going to use the Maclaurin series of sin x. Your un is sin 1 upon n. Now sin x as a series, x minus x cube by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial and so on. So what we are going to do, we are going to replace x by 1 upon n, and that will give sin 1 upon n is equal to 1 upon n minus 1 upon 3 factorial into n cube plus 1 upon 5 factorial into n raised to 5 minus so on, so on, so on. Now here 1 upon n is common out, correct? So 1 upon n, once you have common out 1 upon n, so whatever the bracket term, we are going to ignore it because the highest power of numerator is whatever, but in the denominator you have 1 because the bracket function has a value less than 1. So we are going to ignore it. So Vn is equal to 1 upon n. Now if we are finding the limit, then the limit will be limit un upon Vn, that will be a simply limit n tends to infinity 1 minus 1 upon 3 factorial into n square plus 1 plus 1 upon 5 factorial n raised to 4 minus 1 upon 7 factorial n raised to 6 and so on. N will be cancelled out. And 1 upon infinity will be 0, so you will have value 1, which is non-zero finite. Correct? Again applying the P series, so sigma Vn is a sigma 1 upon n, where P is 1, so it is divergent, and it is divergent, that's why sigma Un is also going to be divergent. Now we are going with one another example. Here see, now this series sigma 1 upon 3 raised to n minus 1 is not in a form of power of n. It is in a power of constant, and that means n is in a power of constant. So un is 1 upon 3 raised to n. So here we are also using the same thing. We are using the dominant power from numerator and dominant from denominator. So dominant value of numerator is 1 and dominant value of denominator is 3 raised to n. So Vn will be 1 upon 3 raised to n. Correct? Now applying limit un upon Vn. So and simplifying that will give you limit 1, correct? And limit 1 you have, that means it is non-zero finite. Now your sigma Vn, now sigma Vn is 1 upon 3 raised to n, is a geometric series with ratio 1 by 3. So that means mod r is less than 1. So mod r is less than 1, so your geometric series is convergent. And geometric series sigma Vn is convergent. That means by limit comparison form, your sigma Un is also convergent. Correct? Now, these are the topics we have seen in this session. Correct? If you have any query or any doubt regarding these topics, then please feel free to contact me. Thank you.